Welcome back, everyone. A new class of solar technology is approaching commercial readiness, and it could significantly change the global energy landscape. Perovskite solar panels, which use a crystalline material known for its exceptional light absorption and charge mobility, are now entering the final stages of development for mass market deployment. Unlike traditional silicon-based panels, Perovskite devices can be manufactured using low-temperature processes and flexible substrates, which makes them faster and cheaper to produce. Research teams and startups worldwide have spent the past decade improving the durability and efficiency of these panels. Recent prototypes have achieved energy conversion rates rivaling or even surpassing conventional systems. With industrial-scale pilot lines now operational in Europe, Asia, and North America, the launch of commercial perovskite panels could begin within the next 2 years. If successful, they may bring solar power to new applications such as windows, curved surfaces, and lightweight installations. Perovskite solar panels operate on a principle similar to traditional photovoltaic devices, but with a fundamentally different material structure. The core of the panel is a thin layer of perovskite crystal that absorbs light and generates electrical charges. When sunlight hits the perovskite layer, photons excite electrons, creating electron hole pairs that move through the material. This process is highly efficient because perovskite has a strong light absorption coefficient, meaning it can convert sunlight into electricity using very thin layers. This allows manufacturers to produce panels that are both lightweight and cost-effective compared to silicon. The fabrication of perovskite panels involves solution-based processing, which requires less energy and fewer steps than the manufacturing of silicon wafers. Liquid precursors of perovskite materials are deposited onto a substrate such as glass or flexible plastic. Techniques like spin coating, slot die coating, or spray coating are used to form uniform thin films. These films are then treated with controlled heating to form the perovskite crystal structure. Because the process takes place at relatively low temperatures, it reduces production costs and allows the use of materials that would not survive the high heat required for silicon panels. Charge transport layers are essential components in perovskite solar cells, ensuring that electrons and holes are efficiently collected and directed to the electrodes. Typically, a layer of titanium dioxide or similar materials is applied beneath the perovskite layer to guide electrons, while an organic or metal oxide material is placed on top to transport holes. These layers are carefully engineered to maximize the movement of charges without energy loss. Their thickness, composition, and alignment are fine-tuned during production to boost efficiency and stability. One of the greatest advantages of perovskite panels is their ability to be stacked in tandem with other solar technologies. A perovskite layer can actually be combined with a traditional silicon cell to form a hybrid panel that captures a broader range of the solar spectrum. In this arrangement, perovskite cells absorb high-energy light, while silicon captures lower energy wavelengths, which results in a higher overall energy output. Such tandem panels have already achieved laboratory efficiencies above 30%, which surpasses the theoretical limits of silicon alone. Encapsulation is a crucial part of perovskite panel design, as the material is sensitive to moisture and oxygen. To ensure long-term stability, manufacturers seal the active layers between barrier films or glass layers that protect against environmental degradation. Advanced encapsulation materials are being developed to maintain performance for more than 20 years, which is comparable to the lifespan of silicon panels. These protective layers must also be transparent, flexible, and lightweight to maintain the advantages of the perovskite technology. Electrode design is another area of focus in perovskite panel development. Transparent conductive layers, such as indium tin oxide or alternative materials like graphene, are applied to allow light to pass through while conducting electricity. On the opposite side, reflective or metallic electrodes collect charges and complete the circuit. Researchers are experimenting with replacing rare and expensive materials with cheaper, abundant alternatives without compromising performance. These innovations are essential for making large-scale production both affordable and sustainable. Perovskite panels can be manufactured on flexible substrates, which opens up possibilities for roll-to-roll production, a bit like printing newspapers. This method actually uses continuous sheets of plastic coated with perovskite and other layers, which are then cut into individual panels. Roll-to-roll manufacturing promises to drastically lower the cost per watt and enable new applications, such as portable power mats, solar-integrated textiles, or even curved surfaces on vehicles and buildings. The flexibility and lightweight of these panels also help reduce shipping and installation costs. Testing and quality control are absolutely critical for scaling perovskite technology. Panels are subjected to accelerated aging tests that simulate years of weather exposure, including temperature fluctuations, ultraviolet light, and mechanical stress. Sensors and monitoring equipment track any reduction in output or changes in the material structure. Based on these results, manufacturers can adjust the chemical composition of the perovskite or improve encapsulation techniques. The goal is to ensure that commercial panels meet international performance standards and compete directly with silicon products. Integration with existing power systems is quite straightforward for perovskite panels. They produce direct current electricity, which can be converted to alternating current using standard inverters. And because they can be manufactured in various shapes and sizes, they can be customized for specific installations ranging from rooftop arrays to building-integrated photovoltaic systems. Electrical connectors and junction boxes are added during the final assembly process, making them compatible with conventional solar infrastructure. This ease of integration reduces barriers to market entry and accelerates adoption once production is scaled. One possible future development in perovskite solar technology is the creation of fully transparent solar cells that can be integrated into windows and glass facades. These transparent or semi-transparent panels would allow buildings to generate electricity without altering their appearance or reducing natural light. Researchers are working on adjusting the band gap and structure of perovskite materials to selectively absorb only certain wavelengths of light, while allowing visible light to pass through. This would make it possible to turn entire skyscrapers into vertical solar farms without affecting their aesthetics. The integration of such panels into architectural glass could significantly increase urban solar capacity and contribute to the development of energy-independent buildings. Another promising direction involves the combination of perovskite solar cells with energy storage systems into a single device. By embedding thin film batteries or supercapacitors within the same panel structure, future solar units could collect and store electricity in real time. This would be particularly useful for off-grid installations or mobile applications where constant access to sunlight is not guaranteed. The lightweight and flexible nature of perovskite materials makes them suitable for use in drones, satellites, or electric vehicles that require compact power sources. Researchers are also exploring self-healing coatings and smart materials that can automatically repair microcracks or repel dust, further extending the durability and utility of next-generation perovskite panels. If perovskite solar panels enter the market as projected, they could become a foundational element in the next generation of renewable energy systems. Their low production cost, lightweight, and adaptability would make them ideal for mobile installations, smart fabrics, and off-grid applications in developing regions. In urban centers, semi-transparent versions could be integrated directly into building materials, turning facades and windows into power sources. Their compatibility with existing solar technologies also allows for tandem panel designs that harvest more energy from the same footprint. As production methods mature and stability improves, perovskites could reduce the global reliance on silicon and diversify the solar supply chain. Regulatory approval, investor confidence, and infrastructure readiness will determine the pace of adoption. If all factors align, these panels may play a central role in accelerating the transition to a distributed and flexible solar-powered economy. Thank you very much for watching. Please like and subscribe.